Hi everyone. Today we're going to talk about high and low pressure systems when it comes to air pressure. So let's get started. What is wind? Wind is the movement of air, and it's caused by two things: differences in temperature and differences in pressure. How do we get differences in temperature and pressure throughout the world? It's because of the unequal heating of the sun, right? The sun does not heat up the entirety of the earth equally. Some places have higher temperature and pressure, some places have lower temperature and pressure, and this is exactly what causes wind. So let's refresh on some things. This is what cold air molecules look like, and this is what warm or hot air molecules look like. Cold air molecules are move much slowly because they have less energy, and that's why they are much closer to each other. In the meantime, warm air molecules or hot air molecules have way more energy, so they move fast and they spread apart more easily. And because of this, since they're farther apart, they actually have low pressure. Pressure is the amount of force being exerted by these molecules. Since warm air molecules are farther apart from each other, they don't have to push away from each other as much because the molecules don't really want to be close together. However, in cold air, the molecules are so close together and they don't like it, right? So that's why they use a lot of pressure or force to push against each other, and that's why cold air has high pressure and hot or warm air has low pressure. So this is a refresher. Low um um when molecules are farther apart, we have low density. They have low pressure, they're not really exerting a lot of force, and they're warmer air has low density and low pressure. Cooler air, however, has high density because the molecules are closer together, and it also has high pressure because the molecules are putting more pressure against each other to move away. And this is what our atmosphere looks like because of that. So, in areas in our atmosphere that has high pressure, those areas will have high density as well, right? So, if we look back, in areas that have high pressure, they also have high density, and the air is cooler. So, cool air is high pressure and high density, and that's why the molecules are closer together. And remember, cool air is high density, so it sinks. And it kind of looks like this. Warm air has low density, so the molecules are farther apart. It also has low pressure because of that. And remember, warm air rises. This is a snapshot of what our atmosphere looks like. Here's another refresher. Remember, the atmosphere, the sun heats up the earth unequally, right? And because of this unequal heating, creating warm air areas, cool air areas, less density, high density areas. And remember, this causes a circulation pattern called convection currents. So here's how it works: the sun heats up the land, the air above the land warms up. I remember warm air has low density and low pressure, so it rises. So as warm air rises because it has low density, it starts to cool. And as the air cools down, it remember cold air has high density and high pressure, and high pressure air sinks. So as this air cools down in the top, the cold air starts to sink back down. And it starts to create the circulation pattern, right? And notice in the bottom here near the surface, this is exactly what causes winds. And you'll also notice that winds actually move from areas of cold air to warm air. Or, in other words, more specifically, winds actually move from places of higher pressure in areas where we have cold air sinking to areas of low pressure in areas where warm air is rising. Why? Take a look at the molecules. In high pressure areas, the molecules are closer together, just like cool air. And in low pressure areas, the molecules are farther apart, just like warm air. Remember, the molecules don't want to be that close together, right? So places with higher pressure, the molecules want to push away from each other towards low pressure areas to gain more space. So remember, winds move from high pressure, such as for cold air, to low pressure, warm air. You have the option of writing this down in your notebook. So here's another thing. Winds move from high pressure to low pressure. Cold temperature molecules are closer together or packed tightly. They're more dense and more pressure. And in low pressure areas, we have warmer temperatures. Molecules are farther apart or unpacked, and they're less dense and less pressure. That's why winds want to move from higher pressure areas to lower pressure areas. Take out your note packet. I believe this is the second page of your note packet, and write this down. Planetary wind belts, meaning the winds, the major winds. throughout our planet actually flow from high pressure to areas of low pressure? Pause this video, write this down. So let's take a look at this map. We have location A and we have location B. We have some isolines, and these isolines or isobars, more specifically, show areas of different pressures. These numbers are different pressures. So, which location on this map do you think is the center of high pressure or low pressure? The correct answer is this. This is an area of low pressure. I know because the pressure or ISO bars show areas of lower pressure numbers, and these areas are higher pressure. These ISO bars are showing higher pressure numbers. Okay, so in which direction do you think wind would blow on this map? High to low or low to high? The correct answer is high to low. So in a map like this, winds always blow from high pressure to low pressure, right? So winds would blow from this area to this area, northwest. Now, which location do you think would be warmer or cooler? The answer is the low pressure area is warmer. Remember, warm air rises and has less density and lower pressure. And the high pressure area would actually be cooler. Cooler area has high density and high pressure. Okay? And also remember that means in low pressure areas like this, the air will actually rise because it's warmer. And in high pressure areas like this, the air will actually sink and it will cause a convection current. Okay? This is a side wave view. This is a top view. Now, let's do a refresher. In which area do you think are the fastest winds? Why? C or D? The correct answer is C. Remember, the closer the isolines are, the faster the winds are, the faster the streams are. Things move faster because your pressure or your numbers are changing much faster, right? So C would have higher or faster winds, D would have slower winds. Now let's talk about something called the Coriolis effect. We've talked about this briefly in the past, but today we're going to go a little deeper. The Coriolis effect is an effect on winds and even ocean currents that are caused by Earth's rotation. The Earth actually rotates or spins like this, okay? And as it spins, our winds are actually also, instead of winds moving straight where they want to move, they're actually deflected to the right side in the northern hemisphere and towards the left side in the southern hemisphere. Let's take a closer look. So, say there are two trains moving this way, right? And there's a person right here and there's a person right here. This person wants to throw a ball to this person. What do you think will happen? Well, let's click auto throw. The ball will move straight to the other person if this person is a good thrower, right? But here's the thing. What if these two people were, instead of on trains going straight, they're going in a merry-go-round like this? Well, let's see. They're spinning and spinning and spinning. Now, this person is trying to throw the ball to this person straight, just like before. But notice what happens. The ball deflects to the right. It doesn't go straight. Instead, it starts deflecting to the right side of the person, right? That's because um the merry-go-round itself is moving. So if you compare this to the earth, say these two people were on the earth, this person is on this side of the earth and this person is on this side of the earth, and this person is trying to throw the ball to this person. What do you think will happen? Well, the earth also spins counterclockwise, just like that merry-go-round we saw. So this person is going to try to throw the ball straight at this other person and watch. Instead of going straight, the ball is actually curving to the right side of the thrower, just like the merry-go-round, right? Look at that again. So the earth is spinning, the person's trying to throw the ball forward, but instead, since the earth is spinning, the ball also kind of moves towards the right side of this thrower. Okay? And this is from the perspective of the North Pole. And so now we were just looking at a ball, right? But in reality, since the Earth is spinning, winds also try to move straight like this. Say this wind in the northern hemisphere is trying to go this way, just straight, and this wind in the southern hemisphere is trying to go this way. But because the Earth spins, notice what happens. Those winds will also curve just like the ball. And notice in the northern hemisphere, the winds curve to the right side of the direction of the pathway of the wind, and in the southern hemisphere the winds curve to the left side. So if you were to point yourself towards this southern area, you would see that the winds uh, are actually curving to the left side in relation to which way the arrow is going. Over here, the arrow is going trying to go this way, but the winds are curving towards the right side of the arrow in the northern hemisphere. And that actually happens all over the world. This is what we call the Coriolis effect, the curving of the winds to the right side in the northern hemisphere and to the left in the southern hemisphere. We're actually going to be revisiting this in the future again. So why is that important? Well, this Coriolis effect moves our winds to the curves our winds, right? To the right side in the northern hemisphere. We're just going to focus on the northern hemisphere today because that's where we live. So winds move from high pressure areas to low pressure. We've already said that. But now let's focus on high pressure areas. We said that in high pressure areas, in high pressure areas, high pressure areas have high density and they're cooler, right? And high density air sinks. So if we look back here, and this is a high pressure area, and high pressure areas have high density, so the air sinks. And we also know that winds want to move away from the high pressure area towards the low pressure area, right? But here's the thing, the Coriolis effect is going to have an effect on this. Instead of the winds moving straight to the low pressure, the winds are actually going to curve to the right side of the direction of the arrow. So if we were to see a top view of this, kind of like this, where this is the high pressure area, the center, and the winds are moving away from the high pressure area towards the low pressure area, the winds will actually curve towards the right a bit. So if the wind is trying to go straight this way, it's actually going to curve towards the right side. If the wind's trying to go this way, it's actually going to curve towards the right side. And it will happen to all those arrows, right? And notice that this causes kind of a clockwise, um, sorry, clockwise pattern, kind of like this. Okay? So here's another example. In high pressure areas, winds are trying to move away. This is a top view. And you'll see that the winds are sinking, right? The air is sinking because high pressure areas air sinks, and it's also trying to move away from the high pressure area. And as it's trying to move away, the arrows are deflecting towards the right side. And notice that this creates an overall clockwise flow. So high pressure areas move clockwise, and we have clear skies in high pressure areas. Because think about it, the air is sinking in a high pressure area. If the air sinks, how is it going to form clouds? Right? Clouds need warm, moist air to rise to form, to take it up and cool down to form clouds. So in high pressure areas, we have clear skies and the air moves clockwise. Here's a good way to remember this. Use your right hand and do a thumbs down to show that in high pressure areas the air is sinking. Curl your fingers like this, and you'll notice if you're using your right hand, your fingers will curl in a clockwise direction, meaning the direction of a clock, right, towards the right side. And that will show you that high pressure areas, the winds move clockwise. Let's go ahead and write this down in our notes. Here's a good way to remember all this. In high pressure areas, the winds move in O H H. How? O stands for outward flow. Winds are moving out from high pressure areas, away from high pressure areas. Winds in high pressure areas have happy weather or dry weather. If the high pressure air is sinking, then it can't form clouds. So in those areas, it's really nice out. It's barely cloudy, super clear skies. High pressure areas are really nice. Now, another way to remember it is heavy air. We know that high pressure air sinks. It's not really heavy, but it's just there to remember that high pressure air is sinking in high pressure areas. And next, you can remember it by hands on a clock. High pressure areas move clockwise. So if we take all the first letters, it becomes O, outward, happy air, weather, heavy air, and hands on a clock clockwise. That's how high pressure air moves. Make sure you pause this video, write all these notes down. Next, let's talk about low pressure. Once again, air moves from high pressure to low pressure. Now we're looking at this area, right? In low pressure areas, the winds are moving towards low pressure, right? So if we were looking at this area from the top view, it would look kind of like this. All the winds are moving towards the low pressure area. But this low pressure area is still dealing with the Coriolis effect, where all these arrows are going to be deflected to the right side. The wind is going to be deflected to the right. So if you're looking at the direction of this arrow, it will actually mm, kind of curve towards the right side of the arrow, kind of like this. So if you were to point yourself towards where the arrow is pointing, your arrow would curve towards the right side of that arrow. Okay? So notice overall when this happens, our winds are actually starting to flow counterclockwise, meaning opposite the direction of a clock. Okay, and this actually forms things like cyclones, hurricanes, tornadoes. Why? Because remember, low pressure air also rises because it's low density. It's taking moisture upwards, up into the sky, and condensing. And so, as it's doing that, it's also spinning counterclockwise. This is perfect. If it's warm and moist enough, it's perfect for things like hurricanes. So, this is what we're talking about, right? Remember, low pressure air moves counterclockwise against the clock, and then creates rainy and stormy weather. Low pressure areas you really don't want to be in. It's super stormy, super rainy, because so much of this air is not only spinning but also rising. And you can also use this trick one more time with your right hand. You can show a thumbs up, meaning the air is rising in a low pressure area. And if you curl your fingers, you'll see that your fingers curl towards in a counterclockwise direction. And this is how low pressure air moves. And now let's write this down in your notes. Low pressure air to remember how they move. Remember ILL. Low pressure air moves inward flow. Low pressure air has lousy or wet weather. Any sort of storms, hurricanes, anything that relates to precipitation and just bad weather, I guess, is related to low pressure. Low pressure is light air. It's not actually light, it's just for you to remember that low pressure air rises. And finally, low pressure air moves left or counterclockwise against the clock. And these images are here to help you. Okay? So overall, this is all we talked about. High pressure O, outward, happy weather, heavy air, hands on a clock. Low pressure ill, inward flow, lousy weather, light air, left clock counterclockwise. If we put all this together, it kind of looks like this. We have an area of high pressure, we have an area of low pressure. High pressure areas move clockwise. Low pressure areas move counterclockwise. But overall, still notice that winds are still moving from high to low pressure. And if we do more of a sideways view instead of a top view, you'll see then that in low pressure areas, winds are moving counterclockwise, but also towards the low pressure area. Winds are also rising and forming clouds and just really rainy, lousy weather. And in high pressure areas, winds are moving away from the high pressure towards the low pressure area. The winds are sinking in high pressure areas. That's why we can't really form clouds, and that's why in high pressure areas it's clear and sunny and nice. And this overall causes convection currents, right? And this is all because of the unequal heating of the earth. The sun does not heat up the earth equally. It's not fair, right? All over the earth. So that's why some places have higher and some places have lower areas of pressure and temperature. Now, what happens in the US? If you go to reference table page 14, you'll find this image. And we'll talk more about this image in the future. But for now, we want to know how the winds overall, generally, our major winds move in the US. So for this, you need to learn the vocabulary word storm track. A storm track is the path of a storm, such as a hurricane, tornado, cyclone, or any type of storm. Okay? Storm track, the path that the storm is going. The US is actually located at around 40-degree north latitude, somewhere around here. Okay? And notice all of our major winds, not all winds, just our major ones, are moving northeast just like this. We'll talk more about why in the future, but for now, if you forget this, it's in your reference table, page 14. And so we would say winds and normal storm track, meaning the track or path of most storms, such as hurricane, tornadoes, cyclones in the US, actually move towards the northeast. If you need to write this down in your notes, go ahead and do so. This is something you should remember. And also write this down right here. So in the US, the normal storm track or path is the northeast. So in the next video, we'll talk about some questions related to this.